And off we go. Alright, so today's lecture is then going to be about hash tables and linear probing. Oh, I should mention, I did put up the videos for last week's lecture, so they're kind of at the end of each chapter, there's some materials. So there should be a link to some YouTube videos. I noticed the audio is a little bit inconsistent. It seems like when I walk over here, the volume goes down over there, so I'm not sure what the point of these headphones are. So I'm trying to figure that out. Hopefully today it's better. Okay. Back to the lecture. Okay, hash tables and linear probing. So let me just remind us what we've been doing up to this point. Our first lecture, introductory lecture, we analyzed restat and quicksort. And really the theme of the day was linearity of expectation. Last Thursday, we did the, we did frequency estimation and we did heavy hitters. And some of the new things we used, one was we started discussing hash functions and particular kinds of hash functions. Last week we just used universal hash functions. Today we'll use even a stronger family of hash functions. And we got to use, finally, Markov's inequality in addition to linearity of expectation. And there the focus starts to become not just what's the average, but how often are we close to the average. That was important, for bounding the error and to do amplification and stuff like that. Okay. All right, so today is kind of going in the same direction tool-wise. So, the algorithms we'll study today are hash tables, the most practical thing ever. And we'll study two kinds. One is called chaining. Maybe you've seen this before. This is a pretty simple one. But then we'll also discuss a more sophisticated, the kind you would actually use in the real world version called linear probing. And that's the analysis that's actually going to require us to learn some new tools to do it correctly. So what we're going to learn, one thing is that universal hash functions were really about pairs of elements, and when they were colliding, we're going to kind of generalize from pairs, and we're going to be looking at something called k-wise independent hash functions for various values of k. And we're going to generalize Markov's inequality, what are called higher moments, but I'll explain that when we get there. But we'll also use something a little bit stronger than Markov's, but similar in spirit. Okay, so that's today's agenda. See how it goes. All right. Okay, so I'm sure you guys have all looked at this web page a gazillion times. Right? This is what I found online for the explaining how dictionaries work in Python. Right? So I'm sure we all know how it works, but the basic principle is we have keys and values, and we set the value of a key. And Python is kind of interesting compared to, say, the previous generation of languages like C++ or Java or something like that, because they just built in syntax so you can just use dictionaries like right away, right, with the curly brackets. You don't have to initialize some kind of hash map with a particular type or anything like that. So you just plug away and you play with it. And so dictionaries are really right at the heart of Python. And last I checked, at least, the object system in Python was basically dictionaries in disguise. It just initializes some default values and you make a new object. It just copies the dictionary over. So, okay, so we see dictionaries as sort of a first-order primitive in Python. Basically why it's popular. Here's maybe the more old-school style. Here's the interface for a dictionary in Java, right? So you have a type for a key, a type for a value. This is also a website I've seen a million times, although I've never read the fine print. So I'm guessing you guys have all seen and used this before. Fine. So we'll study how to implement these things correctly today. So we'll keep things simple. We'll just only worry about basically 3 operations: insertion, deletion, and looking things up. So inserting or set, I want to set, insert k, comma v, is setting the value of k to v. Then later when I look up k, we'll get back v. No big deal. And also deletion, okay, I want to remove it. Okay, so a very special case, and the kind that comes up a lot, for example, in our undergraduate algorithms class, is when you have contiguous keys that are just integers from like 1 to 100. Right? So, okay, that might seem very special, but for example, in one of those like graph algorithm problems, we say, oh, we give you a graph and stuff like that. The first step you can do, given your input, is you can renumber or relabel all the vertices, just counting them off, right? And say, oh, that's vertex 1, that's vertex 2, that's vertex 3, that's vertex 4, right? And we can take our input and assign numbers to everything, or reassign numbers. And now basically our keys are integers between 1 and n, and it only took you linear time to go through it. It's not intuitive, right? So you might do this in a pre-processing step. So this quote-unquote special case does come up. Okay? All right, so in this case, when you know all the keys are integers between 1 and n for a known n, what's the best solution? Yeah. Just an array. Right? Okay, so, sorry. Just an array. Allocate n slots. First key goes in first slot, and so forth. Okay? It's about as good as we can expect. It uses 1 unit of space per key. That's as best possible. And you get constant time access. And non-theoretically, you'll get little practical benefits like it's very compact, you're going to get less cache misses if you're going from left to right, they'll scan very quickly, stuff like that. It's much better than following pointers in a linked list. Okay, so this is the best case. Okay. All right, so this is great, in static settings when we can index the input, reindex the input. When is it not good? Yeah. Sorry? Just in general, just when things are changing a lot, when we don't know all the keys on priority, or inserting and deleting out of the middle, and we have holes and stuff like that. And at least my experience with dictionaries in programming is the only reason I want to use them is because I'm lazy and I don't want to pre-plan anything and I don't want to decide how many keys and values I'm going to have ahead of time. I like the convenience, just figuring it out later. Okay, so then here is maybe a more general case, is that we have n integers, but they're out of a much bigger space. I'll write 1 to u. U stands for, I guess, universe. Okay, and u can be very big. For example, if we're saving strings, right? I can think of each string as a number based on the bit encoding, and now you're looking at ginormous numbers, sort of like last time. Okay. Fine. We could still try using an array for this problem or this setting, right? And of course, you still get constant time access. That's good. But I'm sure as you guys all realize, the problem is that we need massive amount of space, including space for all the keys we don't use. Right? That's really the main drawback, is the space usage. Okay. What's a different data structure then for this sort of sparse setting? Besides hash tables, which we'll obviously talk about later. But what else comes to mind? A linked list. Okay, so we can do a linked list. So if I did a linked list, it would be a linked list. So I guess I'll just list the keys. And if I want to look something up, I'll scan and find it.
I was thinking we could do something smarter where we also order the linked list by...
Okay, I'll sort the linked list in order of key. Fine. Okay. So if I did a linked list, how much space would I need? Of n space. Okay, and if I wanted to do a lookup, how long would that take? Okay, I heard a couple of things. Okay, did I hear log n? Okay, who thinks log n? Okay, one vote for log n.
I do the binary search thing and we say that we sort the linked list.
Yeah, the linked list is sorted. Linked list is sorted. Anyone else for log n?
I mean, if we can use the skip list instead of the linked list.
You're using a linked list? Okay. Any answers besides log n? O of n. Okay, why O of n?
You don't know where the pointers are using this order.
Yeah, you still have to scan the thing. So you can't jump around, so you can't do binary search over a linked list. Okay. All right, any other ideas besides a linked list?
AVL trees.
Sorry?
AVL trees.
Okay, AVL trees, or rather just balanced trees in general. AVL trees, I never remember how to actually implement. Okay, so if you use a balanced binary search tree, there's a gazillion different ones. Besides AVL trees or red-black trees, I sometimes teach just lazy rebuilding. I don't know if you guys have seen that. That's a very simple one. Another very clever one is Splay Trees, where you rotate every time. That has certain nice competitive properties as well. So if you use a balanced tree, so these are trees that one way or another are effectively balanced, even if the insertions are coming in crazy order. What's the space usage? O of n. That's right, because you have a tree with n leaves, so you have n minus 1 internal nodes. And what's the time for looking up insertion and deletion? Log n. Okay, good. Maybe amortized, of course. All right. So then the question of today's lecture, okay, so we can put these side by side, right? For this basic problem, arrays have the benefit of still having constant time access, but the space is absurd. Search trees will give you log n time, which is slower, but your space usage is basically ideal, right? Think of all that. So the question then is, can we get the best of both worlds? Like many questions in the class, the answer is yes, but we're going to use randomization to help us accomplish this. All right, so hashing we talked about last time, so I can probably go somewhat quickly. All right, but the high-level idea is that we have these keys in this much larger space on top, and we're going to come up with some function h, which takes a key, outputs another number, and drops it into a smaller space down below. Okay. And the idea is that, okay, the nice thing is that M is potentially much smaller, much more modest, much more reasonable. But to figure out where to put the key, I'm just evaluating the hash, which hopefully is going to be like constant time. So it's almost like you're getting an array-like performance overall. The only issue, and really the only thing we ever worry about when we talk about hash tables, is that any time we take many things and map them into smaller things, you're going to get collisions. Many things will map to the same thing, no matter what. So of course that was also the topic of last lecture. So again, a collision is when two different keys have the same hash code, right? Okay, good. So, at some level, when designing hash tables, the question is really how do you handle and address collisions? That's your main design point. Okay. You guys might have seen some of this stuff before, so I thought I'd open the floor. What are some ideas for handling collisions when you're making a hash table?
The first can be that you can create multiple layers of hash tables and rehash them again.
Okay.
And another thing can be that you can...
Well, give me one sec. Okay, so we can do, I guess I'll just call it layers, like onions. Onions have layers. So you're saying, okay, let's hash into here, and then if I have lots of collisions, I will hash again into here, something like that. If I have lots of collisions, I guess I'll hash into here. Okay, hashing all the way down. That's maybe an idea.
You can also maintain some like the balance trees and for each bucket.
Okay, so maybe another idea then is I think what you're also kind of describing as a secondary data structure. Okay, so I guess the idea is I have a hash table. If I have many things colliding into one slot, then maybe down here I'll build some kind of elaborate data structure and hope it's in a data structure over much fewer elements and maybe get some benefit. Okay. And at some level you can consider the layers idea sort of as a secondary data structure. Okay, other ideas? Yeah.
You can just scan down to look for an empty spot.
Okay, so that's something that we will be the main topic of today's lecture. So this one it's called linear probing. But let's say that your item is going to go into that slot, but that slot is already occupied. Okay, then we're going to keep looking for the first unoccupied slot and put it there. That's a reasonable way. Okay. All right. Any other ideas? No wrong answers. Okay, so here's the list. Okay, one is we can try to calculate how big the array needs to be. So let's say you have some idea of what n will be like, you just don't know which n. Then maybe you can still figure out roughly how big the array should be. That there are no collisions. Simpler than just putting a binary tree or a balance tree in each cell is just to make a linked list at each cell. We'll analyze that. That's pretty common. A fun one that we won't discuss is called cuckoo hashing. The idea is you have two hash functions. Okay. So for each key, you look at both of the hash locations and see if they're both occupied. I mean, if one of them is unoccupied, then you just put it there. But if they're both occupied, then you might see who's already here, and this person has two hash codes as well, and see if you can bump it to another slot, and bump it and bump it and bump it. So you can use the two hashes to try to kind of make some room.
How can you find them? Like when trying to find the elements, like you have two hash functions and they are indicating two different values. Then
So how do you do lookup?
Yeah.
So lookup k, and I just check both slots to see if k is there. So in the array, you probably want to save k and b, so that you know. In any of these schemes, because otherwise the value just places the hash code, which could come from many different keys. So you probably want to save the key and the value in that spot. Otherwise, yeah. Briefly had a hand? No? Okay. All right, so that's just a fun one. And then again, this one where we scan actually is a very good one in practice and in theory, and that will be really our challenge for today to analyze this. Okay. All right. Okay, so as we do this, just to remind us, so first thing I think we're going to analyze is just the simplest case of putting a linked list at each cell, and we're just going to do universal hash functions. This is really more of a warm-up, and it's probably easier than what we did last time. So just as a reminder, a universal hash function means that the odds of any two elements colliding is as if they were independent. Right, ax plus b mod p is a simple example. Okay, so we're going to analyze this scheme then, which is just to handle collisions with linked lists. So I guess I elaborately drew out what ax plus b mod p might look like, right? But here is sort of that intermediate stage, and then down below is when we actually take the mod f. And the point is just, if I have two keys in the same slot, I'm now going to make a linked list. Those two keys. Okay, so the data structure, when looking something up, is just going to scan through the list. All right, so that means if I'm analyzing the running time of an insertion, deletion, or lookup, then what I'm really kind of interested in, because all the top part should take constant time just to do a little bit of arithmetic. So what I'm really interested in is, what is the expected length of the list of a particular key? That's really going to be the running time of one of these operations. All right, so let's do this together. Okay, so here I'm assuming there's n keys, and I'm hashing into an array of size m. Per computer science tradition, we choose the only two letters that sound the exact same and look the exact same. Okay, so the claim is that it's going to take roughly n over m time in expectation for inserting or deleting a particular key. Okay, so how might we set this up? Okay, let me get us started. All right, so the running time is going to be roughly the length of the list where HK corresponding to HK. So let's say that we want to then analyze this quantity. What is the expected, say, number of keys, I guess, colliding with, let's say I want to insert some key k. Okay. So the number of keys colliding is going to give me the length of the list. That's all we're trying to analyze. And that'll give us our expected running time. Okay? All right. So now what? Fine, but we need to... we usually apply it to a sum or something, right? So let's at least set up the sum. So we need some variables or something. How would I set that up?
And the first indicator variable to indicate whether key I collides with k or not.
All right, so let's write xi is equal to 1 if i's key collides with k, 0 otherwise. Okay, now let me write this as the sum going from 1 to n of xi. Now we can do the... Huh? No, go ahead. You teach me. Linear expectation thing, also known as linear expectation. Okay. Now what?
Property of universal hash function.
Which is? Yeah, it was 1 over k before, but I guess here in our notation now it's 1 over m, and there was n of them. It's equal to n over m. Okay. Fine. So nothing special. This is very similar to what we did last week. Okay, fine. So at some level, though, we already sort of have a constant time sort of performance. If I set m to be roughly the number of keys, then on average you're going to be spending constant time for insertion and removal. All right. Okay, so that addresses then our first easier example of a hash table. And we only have the tough one ahead of us, which is going to be this linear probing hash table. But before I start that, any questions about what we just did? Yeah.
On the group, like the sum, is like technically should the do we need to count k colliding with like itself in the sum?
Well, I figured in the worst case that's going to be off by 1 or something.
Right.
So no, between friends it's fine. It wasn't really clear if I meant that there's already n keys in there or if k was the nth key. It doesn't matter. Okay. All right. Yeah.
Rather than doing it just for excitation, can we do something with high probability?
Can you do something with high probability? Well, okay, yeah, well, let's say based on the tools we already know, you can say, well, okay, so let's say that m is roughly n, so we're looking at a constant time and expectation. What are the odds that it's close to constant time or within a constant factor of constant time? That doesn't really make sense. What is based on something we've already used, how might I upper bound the odds of deviating away from this expected running time? Yeah. Markov's inequality. So the odds of being 2 times bigger than what we expect is at most 1/2. 4 times bigger than what we expect is at most 1/4. Okay. Now, this will become a little more clear up ahead. But we got, with quicksort, we got really strong concentration bounds, right? We said, oh, the odds of being 100 times bigger than n log n is like 1 over n to the 100 or something. It's going down very fast. Okay? We don't necessarily get that here. Okay? Does anyone want to try to guess that maybe the point of weakness or how to strengthen this?
The universal hash.
Yeah, the universal hash does not really give us that sort of full independence we need to get kind of law of large numbers types of situations.
So if we were smaller in case of the hashing,
we would have to strengthen our hash function. Yeah. And one of the homework problems is getting a high probability bound assuming an ideal hash function. So assuming everything is completely independent, which is maybe not realistic for hash tables, but still is useful for other settings, and getting a high probability bound. All right. Okay. Good. All right. So on to any other questions though? Those were all very good questions. All right. Let the party begin. All right. So linear probing, I sketched it out a little bit before, but again, the idea is that what we want to not do is we don't really want to make a linked list appending to every array. It's sort of annoying. We want to keep everything in the array, partly because arrays are just so high performance in practice, right? Like all the constants are ideal. You're never getting a cache miss, right? So the idea on this data structure is that if I want to put x here, but I find it already occupied, then I'm going to start scanning down the list until I find an empty slot, and then I'll put x there. Okay, and scanning, I mean, they're all constant time operations, but this is really a constant time operation. It's quite fast for the computer, already looking at one memory location, to go to the next one. And maybe that whole line of array slots is already filled up in the cache anyway, right? So this is quite fast. All right, so that's how we do insertions. If I want to delete an element x, we have to be a little bit more careful. Okay, so I want to delete x here, right? So first we go in here and we scan and we look for it, and we'd find it. Okay, and I delete the thing. Okay, but one thing we're going to do after that is at some level I want to fill this hole. Okay, it'll become a little more clear why later. But imagine at this stage if I was looking up z. Okay, so if I was looking up z, I would go here, which is I guess is where the hash code is, and I would start scanning, and I would reach an empty slot and conclude that z is not there. Okay, so I want to avoid that kind of thing. So after deleting x and making this empty space, what we do is we start scanning for the next element whose hash code also falls below this newly opened slot, which in this case is z, and we would put z there. And that would become empty. And possibly I would need to fill the slot for z if that was the case, except here we can see that the next slot is empty, so nothing would get filled in. So that's how we do deletion. Okay, so that's the basic data structure. Okay, and when we're analyzing the hash table, the running time it really has to do with kind of how many consecutive slots from where it should be and where it ends up. In the case of deletion, basically until there's an empty slot thereafter. So what we're really going to try to analyze is kind of how long are these runs, how many cells do I have to scan, and that'll be the running time of my algorithm. All right. Okay, so in analyzing this, it always gets a little bit confusing because elements don't really get placed where they're supposed to get hashed. Okay, so I'm going to be careful about the following word usage. I'm going to say that x hashes to a cell AI if in particular the hash code is I. And I'll say that x occupies AI if x is actually in that cell AI. But because this funny data structure, just because x is hashed AI doesn't mean x occupies AI. And just because x occupies AI doesn't mean x was hashed AI. So I'll use those words in particular to try to keep these two things separated. And one convenient piece of notation. So naturally we're going to be kind of focusing on sequences of cells a lot. Right, so I'll kind of use this interval kind of notation, A comma B, to refer to all the cells between A and B, between 5 and 10, something like that. With the additional caveat that if I wrote like 10 comma 5, I mean I'm going to like wrap around. Okay, so if A is bigger than B, I mean kind of A plus 1, A plus 2, A plus 3 until we get to the end, then starting back at 1, 2, 3, which is what the data structure would do too. It's not really drawn, but if you got to the end, you would just go back to the beginning. So you can think of it as like a circle. Okay. Fine. Okay. So the main invariant that we're preserving in the insertion and deletion is that if x, which is supposed to go here, occupies some cell L, okay, It will maintain the invariant that all of these are filled up. And the deletion was designed particularly to maintain this invariant. Okay, so we always have that all of the entire interval between h of x and where it ends up is occupied. All right, that's, I think, the main thing we'll need to carry with us. Okay. All right, so just a little bit of history. So my understanding is that computers used to be very slow and very clumsy, right? You didn't want to do dynamic memory allocation. It's like vacuum tubes or something, right? But we do have things like arrays. So whereas that chaining thing we already analyzed, which is very simple to analyze, making those linked lists is a big pain. Okay? But even on a very old limited computer with very primitive programming languages, this is more or less programmable, right? Because you're just scanning down a list and comparing keys. There's no dynamic memory allocation or garbage collection. Okay, so my understanding is that this hash table has been around for a long time, okay, and has always worked really well in practice. Okay. I'm sure you guys have all heard of Knuth. He's one of the very early guys to analyze algorithms. He sort of brought big O notation from other parts of math and computer science. He's done a lot of stuff. But in one of his memoirs, he said this is the first thing he really analyzed rigorously. Okay, and he analyzed this data structure for ideal hash functions. He wasn't worried about limited randomness at the time. And showed that you get constant time performance when the size of the array is a constant factor bigger than the number of keys. Okay, so maybe in some sense this is the first algorithm to be rigorously analyzed. Okay, so that's very old. That's from 1964. But I left open this question about, what about limited randomness? What happens when you're using more realistic hash functions like universal hash functions and stuff like that? All right, so let me explain then. Okay, so when we talk about limited randomness, up to this point we only talked about like ideal randomness and universal hash functions, which is the very bottom. So this is about stuff that's sort of in between. Okay. So k-wise independent hash functions. It just means that for any k keys, if I'm just looking at the k keys, they are behaving as if they were ideal hash functions. So for any k keys, and if I choose any k slots, any k values, the odds of the first key getting that first value, the second key getting the second value, and so forth, is 1 over m to the k, as if it was completely random. Okay, so bunches of up to k at a time will behave ideally. This says nothing about groups of k plus 1. Okay, so limited number of keys. So universal hash function sort of corresponds to 2, although actually it's even weaker than that slightly. But in general, you can have k is 3 or 4 or log n or square root n or even n. Once you get to n, then you're just looking at an ideal hash function. So at some level, then the question left after Knuth was kind of what value of k can you still get good performance within your probing? Okay, so all right, so it took a long time, but in 1990, it was shown that for log n, y is independent hash function. So roughly any log n keys act as if completely independent. Then you can get constant time. Okay, so that's fine. But then even more dramatic and relatively recent, it was shown that for just 5 y's independent hash functions, we can get constant time performance. Okay, so it's pretty remarkable that, it's always amazing when there's a problem that's open for like 40 some odd years before it gets resolved. Okay. A follow-up paper showed that if you have 4 y's independent hash functions, it won't work. So 5 is actually the right answer. And that's what we're going to try to prove today. All right. Any questions? No. All right, so that's then our theorem. We're going to say, let's let H be 5 wise independent. So any 5 keys act as if independent. Then if M is, I guess I put 8 there, 8 times the number of keys, you get expected constant time for operation. I should probably briefly mention, okay, how do you construct a 5 wise independent hash function? Well, last time universal hash functions was AX plus B. So one way to do 5 wise would be like
X plus
AX to the 4th plus BX to the 3rd plus CX squared plus DX plus E. I think that's 5. Okay. Mod P, mod F. Okay. So the point, though, is that it's, again, a simple arithmetic kind of thing. All right. Okay, any questions about what we want to prove? Oh. Okay. All right, so that's what we want to prove. I need to introduce a few more tools that's going to show up in the analysis. Okay. All right, so just slightly more general than a k-wise independent hash function, we could in general have k-wise independent random variables. That just means, okay, I have n random variables out there, any k of them behave as if they had nothing to do with each other. In the sense that the probability of those k variables getting k particular values is equal to the probabilities taken apart. But again, it says nothing about k plus 1 variables at a time. Okay. Fine. That's no good. All right, so I mentioned earlier we're going to try to do something a little bit stronger than Markov's inequality. And here's sort of the technical tool we'll have to use today. Okay. It's a little bit eccentric. Don't worry too much about that, about the exact details. But let me read it out loud. So let's say that x1 through xn are 0, 1 random variables like heads and tails or something. Okay. But I'm only assuming they're 4 wise independent. So not completely independent or not completely dependent or whatever. There's some independence. Groups of 4 of them at a time are well behaved. And I'm letting mu be the expected sum, the expected number of heads. Okay. Then the claim is that the probability that the sum exceeds the expectation by some factor beta, for any beta you want to plug in, is at most sort of this eccentric 4 mu squared over beta to the 4th. Okay, that seems kind of weird. There's no reason to memorize this. Okay. So let me try to demonstrate by just comparing to what Markov's inequality would have given us. Okay. So let's take beta to be alpha times mu for some parameter alpha. Okay, so let's say alpha is even just 1. I'm saying, what are the odds that's going to exceed 2 times its average? That will be 1 plus alpha mu. Would be 2 mu. Okay. So Markov's inequality says that the odds of exceeding 1 plus alpha mu is at most. Yeah. Actually, at this point, the mu's already been canceled out, so it's actually just going to be 1 over 1 plus alpha. So if it were 2 times the average, it's at most 1/2. So 1/2 corresponds to 1 over 1 plus alpha. Okay. Fine, we already knew that. Now, if I put in this weird thing, and let's assume for simplicity that mu is at least 1, because it's the more interesting case. So we have a relatively large average. The average is at least 1. So in particular, the mu squared term is going to be the bigger one here. Okay. All right. So in that case, we'll get something like 4 mu squared over alpha to the 4th, mu to the 4th. Just plugging in this weird thing. Okay. But let me cancel out then mu squared. Okay, and just stare at this a little bit. Okay. Now, we are going to be interested in the case where mu is not just bigger than 1, but pretty big. Because often we are worried about things getting too big. And what we're seeing here is a couple things. So what are some qualitative differences? Don't worry too much about 4 in the numerator. It's obviously relevant. So one thing is that in the second version, as the average gets bigger, the odds go down rapidly at a rate of mu squared. Okay, so Markov's inequality, we don't benefit from a large average. But down here, introducing just 4y's independence, so a mild amount of independence, we actually get that the odds of exceeding the average by a lot goes down in proportion to the average squared. Okay, so the larger the average, the more concentrated at the average. We'll see this like in much, much stronger forms later on. But this is the general theme of concentration inequality, the law of large numbers. When you get some independence, the odds of deviating far from the average in a multiplicative way actually goes down the bigger the average is. Okay, at some level, the kind of idea is you have a bunch of random numbers that are supposed to add up to a big number. Okay? And so to deviate far from a big number, they sort of have to team up and be in sync with each other, right? And all fail together or something like that. But that's hard when they're required to be independent or somewhat independent. All right. Another nice thing is, alpha to the fourth is better than alpha, 1 over 1 plus alpha, when alpha starts to get a little bit bigger. But the key thing is that we have this mu squared in the denominator. I think that's actually what we'll take advantage of today. All right, so if we have time, we can do the proof, or at least I can sketch out the first couple steps of the proof because it actually uses Markov's inequality. That part in and of itself is kind of interesting, and afterwards there's just some kind of calculations to do. But I want to focus on the data structure and using this thing. I'll write it out on the side so that we don't have to memorize it. But see why it's useful. Okay. All right. You have 25 minutes. Okay, so, all right, so let me define runs formally. A run is just a maximum sequence of occupied cells. Okay, that's what I'll call a run. Okay. Is there anything here? Nope. Okay. So, to set up the proof, suppose I want to insert this element x. I want to insert x. And let's set I to be whatever is the hash code of x. And I'm going to let R denote the run at I, which may be empty if the cell is not occupied. And my goal is to show that the expected size of the run is at most some constant. Fine. Okay, so what makes this okay. What's the right way to do this? Okay, so maybe let me try to do a little bit of intuition at this stage here, because once the solution's revealed, it'll start going very rapidly. Okay, so at some level, here is my element x. It goes to cell I, and then there's a run containing it. Here I'm going ahead and I'm just counting the stuff underneath it as well. We're just going for an upper bound. And I think it's a priori not clear how to even get the analysis started, in my opinion. I mean, at some level I can say, okay, maybe I can try to figure out what are the odds that just this cell is occupied, no one else is occupied. And then afterwards I can try to figure out what are the odds that these two cells are occupied, no one else. Maybe I can just try all the different sequences kind of contiguous sequences around it and try to analyze all of them, take some kind of union bound or something at the end, right? Now, one difficulty that comes up is that at some level, if you end up trying all these sequences, you're going to have to take a union bound over like n things at the end, right? There's so many possible sequences to try to address, or so many different lengths. And so that's why we're going to use this very nice trick, where rather than sort of worrying about all lengths, we're going to try to bucket and only worry about certain powers of 2. Okay, so this is, this kind of doubling trick is not uncommon when trying to prove some things. And hopefully by the end of the proof, we'll see why it was useful to have done this in hindsight. Okay, so let me zoom in a little for us. So, okay, so if I look at this picture, I'm sort of looking at the interval with 1 on each side, so 3 total, but really 1. 3 to the 4 minus 1. Then I look at the interval of length 7 around it, roughly 8 minus 1. I look at the interval of length 15 around it, 16 minus 1. The interval of length 31 around it, 32 minus 1. But roughly doubling. And the only reason we have this minus 1, so it looks nice and centered pictorially. Okay, so I have this notation. I sub k will be this sort of kth doubling in size interval around it. Okay, and one thing nice is that if my run has length at most 2 to the k, then in particular, which interval will it always be contained in, or what's sort of the smallest interval in which R is guaranteed to fit? Just to practice and get used to the notation. K plus 1. You can actually do a little bit better. So I think just by fence never mind. Okay, so it'll fit in I sub k plus 1 if it has length at most 2 to the k. Okay, fine. Okay. Okay. All right, so we're just trying to kind of gradually set up, it might feel clumsy, but remember, we're starting from nothing, right? So if the run has at most 2 to the k, I know that the run fits in this k plus 1 dyadic interval. On the other hand, I know that if the run has size at least 2 to the k minus 1, okay, then the first thing I know is that at least 2 to the k minus 1 items hash into R. Okay. And in particular, hash into I sub k plus 1. Okay? Okay, so maybe the one distinction, the subtlety I'm trying to make here is that, so one issue is that, when analyzing this, is that the items are getting placed in all sorts of weird places, right? Because the items don't occupy where they necessarily got hashed into. But within a run, right, within a contiguous sequence where everyone's filled, any element that's occupying somewhere in the run got hashed somewhere earlier in the run. Okay. So somehow getting this set up is sort of delicate, although maybe easier in hindsight. All right? Okay, so we reached this stage then that if my run is between this particular power of 2, it's at least 2 to the k minus 1, it's at most 2 to the k, then I know that at least that many items have hashed into the interval I sub k. And I wrote I sub k instead of I sub k plus 1. Why? Good question. Okay. All right. Sorry to annoy you guys just a little bit. But I just want to make sure notation is consistent for the rest of time. Okay, so I think if we look at this definition carefully, this says that actually, so here's I, and here would be like I plus 2 to the k minus 1. And inside here, if I get my fence post correctly, you should be able to fit 2 to the k. Oh, no, you should be able to fit 2 to the k minus 1. Ah, okay. All right, so the reason why I sub k is okay is because I think I very carefully wrote this as a strict inequality. So we do get a minus 1, and it'll fit in I sub k. Okay, let me just make sure the notation is consistent. Okay, so I don't think this really matters. The constants would just change at the end, but I want to make it the same as the notes. So, okay, so it actually fits into I sub k, not I sub k plus 1. Now I can write a little bit less. That's fine. Okay, so one thing next. So a priori, I want to say this is what I'm kind of interested in, or this is the kind of quantity I'm interested in. What are the odds that the run is between this power of 2? Okay. But the nice thing is that I've sort of turned it into a statement that's a little bit easier to analyze, because I sub k is sort of fixed, right? Independent of kind of how, it's just a fixed sequence, or a fixed set of array slots. And now I'm just analyzing the odds that a certain number of items fall into a fixed set of slots, right? Which means in particular, I'm not really as worried about this whole like hashing versus occupying and what the data structure is doing, how things are getting swapped anymore. I'm now just worried about, here's some slots, here's some items. What are the odds that too many items go into too few slots? I bungled a little, but it's okay now. Okay, so, all right, so I want to analyze the probability that so many items will go into so many slots. All right, so fine. What might be the first step towards such an analysis? Well, we're closer to the end than you guys realize. Yeah.
The first comes expectation of the items, and then you hash it.
Yeah, let's start with the expectation. So, okay, so what is the expected number of items that hash into ik? Okay, that seems like a reasonable place to start. And how might we go about this? Sorry? Yeah, we've already done this. So we'll make some random variables. X sub I is equal to 1 if the ith key falls into I sub k, 0 otherwise. The expected value of x1 up to xn, right? Well, by linear expectation, I'll skip the part. I'll skip some writing. So each of them will fall into I sub k. Each of them are sort of uniformly at random among the m, right? So each of them are going to fall into I sub k with probability I sub k, decided I sub k over n. And meanwhile, I sub k had size, I wrote it down here, 2 to the k plus 1 minus 1 or something. Okay. All right, you guys can see that too. Okay, so that's how many we expect to fall into I sub k plus 1. And we had set n to be 8 times n, or at least 8 times n. So, at most 2 to the k minus 2, say. Right? Okay, so, fine. So we have that. The expected number of items that hash into ik is at most 2 to the k minus 2. All right, now I want to analyze what are the odds that it's at least 2 to the k minus 1. What might I do? So if I use Markov's inequality, what would I get? One over what? Well, we know the average is at most 2 to the k minus 2. And now here I'm doing roughly 2 times that, 2 to the k minus 1. So Markov's inequality, if I had applied it here, would give me at most 1/2. Okay, so Markov's inequality would have given me 1/2. Okay? This is not strong enough for us. It's not, it turns out, strong enough. Okay, so what are we actually going to do then? Okay, so here then is the part where we actually use the 5-wise independence and the 4-wise independence and stuff like that. Why did I have to use a 5-wise independent hash function? So in this analysis, we've already fixed x and we've already fixed the hash code of x. So in terms of the 5-wise independence, that's one of your wises, or whatever that is. Okay? That's one. So the remaining variables, conditional on x being fixed, the remaining variables are 4-wise independent. Okay? And that lemma I introduced earlier was very specific to 4-wise independent hash functions, and we're allowed to use it. Okay, so somewhere in this margin, we have this thing. Okay, so let me just copy and paste this so we can use it. All right, hopefully you guys can see it. Okay, all right, fine. So if we plug this in, and we use the strengthened inequality, which again probably just mostly appears as eccentric at this point. But if we use it, okay, so we get 4 times, okay, this is no good, I'm just copying it. Okay, so this was mu plus beta, so beta would be 2 to the k minus 1 minus mu to the 4th, where mu corresponds to that quantity. Okay. All right, so mu is at most 2 to the k minus 2, right? So 4 is not very important. So the mu squared term becomes big. I'm going to replace mu with 2 to the k minus 2, in which case the squared will dominate the not squared one. Okay. And down here, I can also replace mu as 2 to the 2k minus 2 to the 4th. Okay. Now 2 to the k minus 1 minus 2 to the k minus 2 is equal to 2 to the k minus 2. So we'll have the same thing in the numerator and denominator, and we'll just cancel out the corners. Okay. So this lecture is a bit more arithmetic and mathematical than the previous ones. Okay. But look, this is great. Before, Markov's inequality only gave me 1/2. Fine, it's better than nothing. But the stronger inequality gave me something inversely proportional to 2 to the k minus 2, which is roughly the length of the run that I'm interested in bounding. And not just 2 to the k minus 2, but 2 to the k minus 2 squared. Now, eventually we want to say, oh, I don't want my run to be very big with high probability. I'm really worried about long runs. So I'm really interested in the case where this is big. And the bigger it is, the more worried I am. Right? That's going to kill my running time. But the bigger it is, the odds go down even faster. So if I put the size of R up here, that cancels out one of these terms, right? Because one of these is roughly the length of R that we're interested in. Then I'll still get 1 over R in the bottom. Right? Kind of an expectation, actually, the longer runs are adding less to my expectation. Okay, so that's the idea. So that's why we needed more independence and a stronger inequality to sort of cut off the bad tail. Okay. So what does that look like in terms of calculations? All right, so my expected running time overall is the expected length of the run R. Okay. And just linear expectation says, okay, for each value of L, what are the odds of being that value? Okay. All right. So here then is where that doubling trick comes in. That's so valuable. Okay. So what we're going to do is, because initially here I have all the values of L from 1 to n or something like that, right? And but what we're going to do is, it seems sloppy, but it turns out to be very useful, is that we're going to bucket and sort of like round up in powers of 2. Okay, so I might say 2 to the k times the probability that R is at least 2 to the k minus 1 and at most 2 to the k. Okay. So I'm sort of rounding up, right? So if R had some value between 2 to the k minus 1 and 2 to the k, maybe closer to 2 to the k minus 1, closer to the lower end, I'm still paying 2 to the k for it. So it's rounding up to the next power of 2. Okay. That might seem bad. Okay, but now we can apply this bound we got here. Okay. There's a 4 out here. 1 over 2 to the k minus 2 squared. Okay. All right. And then from here, you guys can probably take it away. But I guess we have a 2 to the 4 overall there. So we'll get some 4 times 2 to the 4. And then what's left is 2 to the k divided by 2 to the k squared. One over 2 to the k. Do the calculations make sense? I know I'm going a little quickly, and calculations are no fun. Now, what's the last sum? What does it all add up to? Yeah, in fact, what constant? 10? What's 1/2 plus 1/4 plus 1/8 plus 1? Okay. Right, because you start with 1 and you split it in half, and you split the remainder in half and split the remainder in half. Okay. All right. And then I guess you have times 4 times 2 to the 4th or whatever. So we have some 2 to the 6th or something expected overall. Okay. Fine. So what's going on here? Okay. So at the end of the day, then we've shown that the run is at most constant. All right. So that was a more complicated proof than we did last time by far. Including tricks such as these dyadic intervals, and trying to figure out how to get things to double and cut off the tail. What we're able to achieve at this stage was we sort of got this kind of polynomially decreasing thing depending on the length. Okay. I only want to briefly point out in the proof of this important lemma why we used 4y's independence, and then I won't do necessarily the remaining calculations which are in the notes, and you guys could figure it out yourself. Yeah, question?
When we analyze the training time, they only use 4 elements, 4y's independence. Why is it not true for 4y's independence?
Why is it not true for 4? Well, I think that's a little more complicated to explain where 4y's breaks, but I can explain why we needed 5y's. It's because we are inserting one element, and then the rest of the analysis is conditional on inserting that element. So I'm inserting x to here.
Oh, you fixed x.
And I fix x, and now conditional on x, if they were 5y's independent, the remaining values are now 4y's independent. Okay, so this will only be quick. Okay, so let me just briefly explain why 4y's independence suffices, and also why this is to some extent a consequent of Markov's inequality. Because it's going to demonstrate something called the moment method. Okay, so if I want to prove something like this, the sum being bigger than mu plus beta. Okay. All right, so what we can do to sort of ramp things up, okay, is we can apply functions to both sides. So something that we'll do in a different class is, I can look at, what are the odds that if I exponentiate this, I'm going to be way bigger than the expectation or something like that, right? Sort of putting it on steroids. That'll lead to something called Chernoff bounds, which we'll do later. Here we'll do something weaker, but appropriate for 4y's independent random variables, which is I'm going to take the 4th power. Okay, it's a little bit more convenient to subtract the expected value first. Okay? And to this quantity we'll apply Markov's inequality. So if I apply Markov's inequality to the 4th power, then I'll get something like this. Okay, so you see the beta to the 4th already appearing in the denominator. But I haven't explained why 4y's independence is useful yet. So we have to look at the numerator for that. Okay, so this quantity So let's say for simplicity, all of these random variables were identical. They all flipped heads with probability p. You can generalize it to where they have different p's for different i's as long as the average is the same, but I just want to keep it simple for us. Okay? So I'm looking at this 4th power, which is the expected value of the sum. So I can break up the overall average into n copies of p. Right? So I'm looking at something like this. Hopefully my notation is legible. The sum of 1 to n of xi minus individual probability. Okay. So this is describing a polynomial of degree 4 inside the expected value, right? So, if you expand this out, you're going to get terms like, x1 minus p to the 4th. That will be one of the terms in the polynomial. Another one might be x1 minus p cubed, x2 minus p, or something like that, right? Another one might be x1 minus p squared, x2 minus p squared, and stuff like that. So if you expand out the polynomial, you get all sorts of terms like this with different coefficients in front. It might be 1, 4 choose 2, 4 choose 3, etc. Right? And you would apply linear expectations to all sorts of these things. So another one might be x1 minus p times x2 minus p, x3 minus p, x4 minus p, or something like that, right? So you expand out this polynomial and you get all these terms. Okay, so this is now finally where four-wise independence would come in, is that each of these expectations over different x's, I can break them up. Okay, so like an interesting one, take the second column, the second row. Something like this, right? You can break it up because four-wise independent, there's only two terms there. Well, what's this equal to? 0. So actually all of these terms in a monomial are 0. They don't contribute anything. So that's great for us. Likewise down here, I would break this up. I get x expectation x1 minus p, expectation x2 minus p. Those are all 0. Okay, because you can start breaking things up and things start zeroing out. And you're only left with like this term and that term, and then you add it up and you get that smaller numerator. Okay? So the only reason we need a four-wise independence, in general, taking higher powers before applying Markov's inequality is going to strengthen Markov's inequality. You're going to get, in general, better bounds. The only issue is you start getting more interactions among the x's from these higher polynomials, right? Each time they're multiplying each other. They're messing each other up. So we only went up to a large enough polynomial, A, to make the proof of our data structure work, because otherwise, and we chose the minimum kind of hash function needed to allow us to deal with this. That's the high level thing, and otherwise the calculations are. Okay, that's all. Thank you.